Okay, so it's my pleasure today to be the chair of this first session here, and also my pleasure to introduce Vera. So maybe first of all, for those of you who don't know about MoCaO, it's the organization putting on these lectures here. It's the mathematics of computation and optimization special interest group of the Australian Mathematical Society. And the mission of this interest group is to promote the activity in the field of optimization and computation in the broader sense. Yeah, the MoCaO Lecture series is an annual event that was initiated in 2022 with a series of topics in data science given by Stephen Wright from the University of Wisconsin-Madison. And last year, we hosted James Saunderson from Monash University, who talked about polynomial optimization. And yeah, this year we continue the series with our MoCaO lecturer, Vera Roshchina from UNSW Sydney, who will talk about convex geometry. And yeah, this is a rich and fascinating area. I hope she can convince you all. Yeah, this series will introduce the theoretical tools and notions of convex geometry that stem from or are applicable to the problems of modern convex optimization. It will cover the facial structure of general and structural convex sets in Euclidean spaces, as well as in general vector spaces. So this lecture series is really designed to be accessible to novices in the field, so experts be aware. Yeah, and now let me introduce Vera. So Vera is an associate professor in the School of Math and Stats at UNSW Sydney. She received her PhD from the City University of Hong Kong. And before joining UNSW in 2018, she was an ARC DECRA Fellow at RMIT University and held postdoctoral positions at the University of Marin, Federation University Australia, and University of Évora in Portugal. Yeah, welcome, Vera, and thank you so much for being our MoCaO lecturer in 2024. Over to you, Vera.
Thank you very much, Mareike. Thank you all the organizers for setting this up and for inviting me. So as Mareike already explained, I'm going to talk about general convex sets and their faces. So it's a view of convex geometry that sort of I have, right? So it will include some topics, not some other topics. For example, I'm not going to talk about volumes of convex sets. And of course, also just basically repeating what Mareike said is that we have 3 lectures. So I will give the first 3 lectures, and then the next 2 lectures will be given by Isabel Shankar and Bruno Lorenzo. So they will expand on some of the things I'm talking. And also, my goal is to be quite basic. So I'm going to go over some basic ideas that give an introduction to this area, show you some calculations, how we do those things, how we look at convex sets and their structure. So the first lecture will be about just convex and conic problems, faces of convex sets. I don't think the first lecture will have anything that is kind of cutting-edge research, mostly old things that some of you know very well. And maybe for some of you it will be interesting. For some of you it may be something that you've seen but didn't actually look at into details. And also feel free to use the chat, just the meeting chat, if you have any comments, in-depth comments, or just basic comments, or any questions, just use the chat. I have the chat running next to my slides, so I will be reading the chat if you have any questions or anything like this. So today we'll talk about the basics. Tomorrow I will talk about constructing convex sets with desired facial structure. So it will be more related to research I'm doing with my collaborators. And the last lecture will be about convex sets in infinite dimensions. So I will talk about what happens to convex sets right, when we work in general vector spaces, so we don't have topology, and also a bit about topological vector spaces. And I will mention also projection methods and things like this. All right, so then I believe that Isabel will continue with talking about duality, dual representations of polyhedral sets, but she will, of course, explain more about the lectures. And Bruno will talk, I think, about facial reduction and topics like this, if I'm not mistaken. But please correct me if I'm wrong. All right, so let's start. And let's start with basic ideas about convexity. So just a reminder why convexity is important. So of course, should probably move this. And that's okay. Why convexity is important? Of course, it's a fundamental property, right? And I'm talking about convex sets predominantly. Fundamental property used in a very wide range of mathematics and applications, pure mathematics, applied mathematics, and geometry, of course, right? So, of course, in optimization, and optimization models, continuous optimization models, convexity is extremely important because we know how to solve a lot of convex problems. We know how to formulate optimality conditions. Such problems work with duality very well. Such problems work with certification in a sense, right? So we can certify that we found a global minimum or global maximum of a problem like this. What I like about convex sets is that somehow convex sets, and studying the properties of convex sets, that reveals a lot about the geometry of the space in which we're working. And this will be especially clear when we will look at convex sets in infinite dimensional spaces. Convexity works with duality. And again, because it's a very basic lecture, I'm going to show some very simple trick, or let's say some very well-known trick, how you see that convexity works with duality, right? So going from Lagrangian duality, basic Lagrangian duality to convex duality. And of course, many important open problems involve convexity and convex sets. So I'm going to start with a well-known sketch about linear programming. First of all, because linear programming is something that I think everybody who works with optimization in any context knows very well. And also linear programming showcases how we can go from a very basic model or even something very applied and something that is something that everybody is using to amazing mathematical complexity, to unsolved mathematical problems that are extremely difficult and somehow that underlie this model, linear optimization, linear programming model. And that is somehow the case for many convex problems, that we have an applied problem, very useful, very applied problem or very applied model that is convex. And there will be a problem of we don't know why the method doesn't converge, or we don't know how to formulate some problems, some other problems that look like that problem in terms of that problem. And we don't know. And quite often that can be formulated as a pure mathematical problem that is a hard mathematical problem that ostensibly has nothing to do with the application. You can forget about application and just look at it as a pure math problem. All right, so let's continue. So again, something that everybody would recognize, right? So let's look at the linear programming problem, which is a very basic, probably the most basic continuous optimization problem, right? Let's say non-smooth continuous optimization problem. So we're maximizing some linear objective function subject to linear constraints. So of course, there could be different sets of constraints. So in this case, we just have a bunch of linear inequalities, right? So we have this matrix A that is living in R, what would it be, M, let's say M times N, B in Rm here, C in Rn. So we have a linear constraint, we have a linear objective function and a bunch of linear inequalities that constrain the region over which we're optimizing, right? So each one will be something like this. Right? just a linear constraint. And then already we can see the geometry emerging right here. So if we think about what actually happens geometrically for linear programming problems, we have some gradient vector of the objective function, right, that defines the objective function. And what we're looking for is for the maximal phase that corresponds to that direction, right? So the optimal solution or a optimal solution to this problem would belong to a phase of a polytope or a polyhedral set that is bounded by, right, finitely many half spaces, so finitely many hyperplanes. And that's the phase that contains solutions. It can be a facet of a polyhedron, can be a single point, it can be an edge. And in an optimization problem like this, we will be looking for some point right in that phase. So that's a basic geometry that will be expanded upon, right? So then I'll talk about phases of general convex sets, which are, let's say, more sophisticated than phases of polyhedral sets, even though phases of polyhedral sets are difficult enough to have a lot of open problems related to that. Okay, so please, if anybody has any questions or comments or corrections, just use the chat to write them down. So now, of course, you know that linear programming is a model that is used in a vast number of applications. There's very efficient solvers for solving linear programming problems. And generally, we get very good practical, right, solutions, very fast solutions for a very large number of variables. However, even though there's methods for solving linear programming problems, like the simplex method, that is still one of the most popular methods for solving this problem. Interior point methods, there is still no strongly polynomial algorithm known for linear programming problems. So if we want to find a method that will give us a solution to a linear programming problem, or even if we want to solve a decision problem that tells us, is this problem feasible, right? Can I actually find a point that satisfies the system of inequalities? We don't know if there's an algorithm that will tell this in a number of steps, polynomial in the size of the problem. We know that, say, interior point methods are polynomial in terms of the input. So if you look at the bit size of the input, then right, the encoding of the problem, then we know that the problem is polynomial in the number in that size. But in terms of the dimensions of the problem, the real number complexity model, we don't know if there's a polynomial method to actually solve this problem. So you know that simplex method that basically goes from one vertex to another, right? It's following a path from some feasible solution to the optimal solution by following the edges of the polytope, that there's examples for every version of the simplex method known. There's examples that show that it can take an exponential number of steps, a very large number of steps that is not polynomial. But also there's the smoothed analysis of this method by Spielman and Teng that shows that, well, those examples are unstable, right? You can perturb them and then get the good performance of the simplex method and so on. So anyway, this is a practical problem and already a problem in complexity, right? To find a polynomial method strongly polynomial method for linear programming. But what I'm getting to is that, again, it's a well-known, right, kind of demonstration of how we get from practical problems to something very purely mathematical, is that we don't even know if a polytope, which is a bounded polyhedral set, has a shortest edge path between vertices that is polynomial in the dimension of the polytope and the number of inequalities that define the polytope, right? So if I take any polytope and I use as parameters the number of inequalities that defines it, right? So it's finitely many linear inequalities. And I think about the dimension of this polytop. So it will be just the smallest affine subspace where this polytop leads, just the natural dimension of this polytop. We don't know if there exists a path between any two vertices that can be bounded by a polynomial in the dimension and in the number of inequalities, right? So we can define things explicitly. We can define the combinatorial diameter of any polytop, which is the length of the shortest path, maximal length of the shortest path between any two vertices. And then we can take the maximum over all polytops of this dimension and define by that many inequality. So the best bound I found in the latest literature looks like this. So, and we know that, say, the bound n minus z in terms of number of inequalities should be n here. And the dimension is, we know that it's larger than n minus z. We know that it's bounded by this, but still we don't know if there's a polynomial bound. Right? So it's just a snippet that shows how convexity in a very simple setting and the need to solve, practical need to solve optimization problems leads to something that deep, right, and mathematical. So let's move on to general convex sets. So far, any questions or any comments on this? Okay, I hope that at least somebody is listening, because there's no faces on the camera and there's nothing in the chat. So I hope that I didn't bore everybody yet. All right, so let's look at general convex sets. A quick reminder of the definition, right? So we have thanks very much, Arvind. It's really great to see something in the chat. Okay. Thank you, guys. Okay, so let's continue with convex set. Right, so a set is convex. It's a subset in general of a general vector space, right? It's convex. But for now, for this lecture, we are in Rn, and we're using the most, well, let's say basic setting, because we really want things to be understandable quickly, right? So without thinking about generalities. So set is convex if I can take any 2 points in that set, right? And if I connect those 2 points with a line segment, the line segment should be inside the set, right? So if I take something like this and I connect 2 points with a line, then this point is not in the set, so it's not convex, right? And we write it in this way. So if I take x and if I take y, then of course anything in between x and y can be represented as a convex combination of x and y, right? So some parameter alpha will go from a 0 to 1. When it's 0, then I'm here. And when it's 1, I'm here. Recall that a convex hull is just, let's say, a generalization of a convex combination of 2 points. So let's say a convex combination of several points is a generalization of this, right? So we take the sum of some points in a given set with some convex combination coefficients alpha I. And here we just want alpha I to be non-negative and the sum of alpha i's to be 1. So if some set is not convex, we can always convexify it by taking the convex hull. If the set is convex, then its convex hull coincides with the set. It's also the smallest convex set that contains the set. Okay, so we know that some basic things are true about convex sets. It's some kind of basic calculus, right? So intersections of convex sets are convex. Linear images of convex sets are convex, although there's problems with linear images. Linear images means that we think about a linear mapping between 2 vector spaces or 2 finite dimensional vector spaces, and we'll look at the image of a convex set under this mapping. For example, a projection is that kind of mapping, right? So they're convex, but there's a problem that maybe closeness may not be preserved. and some other important things may not be preserved. So I will be talking about spectrohedra and say projections of spectrohedra, not spectrohedra. So some properties may be lost, but we'll always preserve convexity. So of course, convexity comes from an infinite variety of applications in pure and applied math, and it's just a fundamental property that comes up in many fields. But generally, like the most basic ways where the convexity comes from, or where convex sets come from, is traditionally from convex hulls, right? So I have a bunch of points, or I have some subset of the real vector space, and I take the convex hull. Sublevel sets of convex functions are very important, especially in optimization, right? So I'm not going to talk about convex functions, but right, if you have a convex function, then f of x less or equal to something is the sublevel set, and those sublevel sets are always convex. And in fact, when convex sets are defined like this, you can kind of get a handle of that for that convex set from this function. So it's a very useful representation. And what is very popular, and the model that I guess James was talking about last year, is algebraically defined regions and their intersections. So it happens that for a lot of modern applications, when we formulate those applications, those applied problems as convex problems, the feasible region cannot easily be described by, say, inequalities on convex functions. So we have complicated objects that are convex and algebraically defined, like the cone of positive semi-definite matrices, for example. So that's also a very important area, and it's a fun area to explore as well. All right, so let's talk about faces. And please, any questions or comments, use the chat. So now, a polyhedron is a very basic example of a convex set, even though, as we've seen, there's open problems on polyhedra. And the polynomial Hersh conjecture that is asking for a polynomial bound on the diameter, combinatorial diameter of polyhedron is not the only problem, right? There's a lot of problems in convex polytopes. And one of my favorite ones is the Dura conjecture, right? Whether you can find net or unfolding of a three-dimensional polytope. So it's like if you have a cardboard box, right? You assemble a cardboard box from a flat piece of cardboard. And the question is, can you assemble every polytope from an appropriately defined kind of unfolding or kind of piece of cardboard? And that question is still open. Right, and it's also not a combinatorial question, but let's not talk about everything. So anyway, when we talk about polyhedral sets, and if you don't work with faces, I think sometimes it's difficult to go from polyhedral sets to convex sets because faces are a little different. They seem to be obvious, but there's some subtleties, right, in the way faces work for polyhedral sets and general convex sets. Well, one thing that is not so subtle is that for polyhedral sets, we can split them into vertices, edges, and so on. And the number of those things will always be finite, but it's not the case for general convex sets. So for polyhedron, a face is always an intersection of a polyhedron with a supporting hyperplane. The supporting hyperplane is just a hyperplane such that the convex set sits on one side of this hyperplane. Some people would define a supporting hyperplane as something that is actually touching the set. Some people would define it as any hyperplane such that the set is just on one side in one of the half spaces. So for a polytope, every face is defined by an intersection with this hyperplane. And that was also the picture. The picture earlier also showed that those faces are somehow always solutions to some linear optimization problem, right, of a polytope. So this is not true for a general convex set because faces may not be exposed. And general convex sets have let's say most problems that happen with general convex set that we have to use unavoidably, because not every problem can be usefully formulated as linear programming. A lot of problems, I would say most problems, come from the fact that faces are not exposed. So why can't I define faces of a face of a convex set like a polyhedral set? Because we may not be able to slice everything we want of the convex set by hyperplane. So we define a face of a convex set in a slightly different way, or in a very different way, algebraically. We say that the subset F of a convex set C, the face of C, is F is convex, and for any 2 points in C, such that X, Y, and C, such that the open line segment connecting those 2 points intersected with F is non-empty, we must have the entire line segment in the face. Right? So for example, on this set, if I look at a line segment here, it will be a face, right? Because if I pick any line segment inside the set C, right, this line segment wouldn't work, this line segment wouldn't work. Only something like this will work, and if it intersects, right, the face F at an interior point, it has to be inside the face F. So we have some basic relations on faces. We know that the empty set is a face of a set C. The set itself is a face. We also know, and that's very valuable, that faces are faces are faces. And also, if I have a subset, convex subset of some face of a set C, and I should say here, F is a face of C, and that subset is also a face of C, then it's a face of a face, right? So there's very consistent structure of those faces. And we say that a face is exposed if it can be exposed by a hyperplane. So you see on this picture, this particular face is not exposed because in this case, it's not a hyperplane. I have to find the line such that this line will support the set. So the set will be on one side of this line, but the only point that this line will slice off the set will be this point here, right? So I have kind of half a disk joining something like a rectangle, and it's impossible, right? Whatever I try to do here, I'm not going to succeed. All right, so if every face is exposed, then the set C is called facially exposed. So tomorrow I will talk about other properties that of convex sets and faces that kind of build on this idea, right? So the fact that the set is not facially exposed, convex set is not facially exposed, that can only happen for non-polyhedral convex sets, right? So that's the main problem with non-polyhedral convex sets. So there are some basic examples of faces and not faces. So, right, so something like this is a face, a corner or a vertex of a square is a face, edge is a face. Something convex, but something that looks like this is not a face. Also, something like this is not a face of the set, right? So if I take a disk, the faces will be the disk itself, every single point on the boundary, the empty set, but something like this will not be a face. And there's some other examples here. Again, I think I will show this picture later tomorrow, and I will talk about specific ideas related to faces of this set. So with red on these pictures, I have just shown some faces, right? So like Euclidean ball, faces of the ball itself, and points on the boundary, and so on. Okay, so I would like to show you how this stuff works with some algebraic objects. So I would like to actually work out the faces of the cone of positive semi-definite matrices, because these things look kind of very trivial when we just think of, oh, let's look at those sets that we can draw in 2 and 3 dimensions, right? Whether they're faces, it's obvious, we can see them. But when we work with some convex sets that are defined algebraically, actually we have to use the structure of those algebraic objects to work with faces. And with every different object, somehow it's different things that we're using. And it's very interesting to see how faces can be identified, calculated, right? How to distinguish between exposed faces and unexposed faces. And we can think about a lot of different objects. So this is the cone of positive semi-definite matrices is the most basic example. We can think about cones of non-negative polynomials, cones of sums of squares, which are convex cones, so they're convex sets. We can think about their faces, and then we'll have to use things like roots of polynomials, points at which varieties, points at which polynomial derivatives are zero, and so on. We can think about hyperbolicity cone, for example, and then there's a completely special and different way to look at faces of hyperbolicity cones, because hyperbolicity cones have associated derivative cones, and we can look at intersections of boundaries of those cones and figure out faces. So there's usually some kind of, when we look at structured problems, there's usually some kind of a structure that hopefully allows you to deal with faces. So let's look at the faces of of the cone of positive semi-definite matrices. And this is a very classic, very old result, right? I just want to do some calculations, show some calculations. So now we are in the space of real symmetric square matrices. And we'll look at the matrices that are positive semi-definite. So of course, a matrix X is positive semi-definite, so it's symmetric, right? So if I take X transpose, it's the same as X. So X transpose is X. Square and by n, I guess it's clear. They're real, so all entries are real. And positive semi-definite means that for any vector that I pick from the n-dimensional space, U transpose XU will be greater or equal to 0. So when I think about the set, it's convex. It's the set of all such matrices that are positive semi-definite is convex in the space of symmetric matrices. And it's also a closed convex cones. And these things are very easy to prove. So they're quite trivial to prove, right? You just take sum of two positive semi-definite matrices. It's easy to see that the sum is positive semi-definite and so on. But a fairly non-trivial fact, and again, it's something very well known, is that all non-trivial faces of this cone are linearly isomorphic to low-dimensional cones of positive semi-definite matrices, right? So any face of this complicated objects that I pick is in a way the same as a lower dimensional cone of positive semi-definite matrices. And one way to write it explicitly is like this. So the only non-empty faces of this cone are the zero matrix and something like this. So I fix some non-singular n by k matrix, and then I look at all matrices that can be obtained like this. So I take all matrices from a lower dimensional cone of positive semi-definite matrices, and I just plug them in this formula, right? And it's that will give me a face of that cone. So let's quickly work this out. So at first I'm just going to show that these things are faces, and then later on we'll have to finish this using some other things related to convex sets. Okay, so I'm going to use two things here. The first thing, let's see. Yes, so the first thing I will use is like this. If I have a real matrix that is symmetric and a positive semi-definite, well, if it's just symmetric and real, then I have the Jordan normal form in a very special way. So because all eigenvalues of this function of this matrix are real, right? The decomposition will have the diagonal matrix in the middle with real entries only, right? And then if the matrix is positive semi-definite is equivalent to having non-negative eigenvalues, and it actually follows from this decomposition. So anyway, So if X is positive semi-definite or X is positive semi-definite, if and only if I can represent this as this. So should I use, I'll use this different notation, so not confused with this, say M, L, M transpose. So this guy is the matrix of eigenvalues. So it's a diagonal matrix of the eigenvalues of the matrix X. And these guys, well, this guy is orthogonal. And the second thing that I'm going to use is that if I have for some vector, if this is 0, then this is also 0. And this can be obtained from the decomposition. All right, so let's see that these things are faces of the cone of positive semi-definite matrices. At first, let's see that 0 is a face. Let me skip 0. Let me just let me skip 0. Let me just show that something like this is always a face of the cone of positive semi-definite matrices. So what I need to do, I need to use the definition of a face. And by the definition of a face, if I have any line segment that intersects what I'm proving to be a face at some interior point, then this line segment should be inside the face, right? So I have my face that I'm proving to be a face. And then if I have any line segment in the bigger set C, right, and it intersects this face F at an interior point, I cannot have something like this. I have to have everything inside the face. So if I want to check the definition of a face, then for any two Y and Z in C, in the cone, Sn plus, I should have, and such that, let's say 1 minus alpha Y plus alpha Z is in, let's put the semi-definite cone here, and plus. Such that they are in the face. I should have Y and Z in the face, so I could just show that Y is in the face. Right. So, and let's do this. So suppose that it happens that I have this. So then, let's say this will be X. So now, if I'm going to use that matrix Q in the representation. So now, if some point P such that Q transpose P is 0, then P transpose XP is also 0, right? If I substitute this, if I substitute X here, I will get this relation. So then I conclude that 1 minus alpha P transposed YP plus alpha P transposed ZP should be 0. And because this is non-negative and this is non-negative, I conclude that both of those things should be 0. And so by something that I have before, by 2, I have YP equals 0. So from here, I conclude again that so P is in the kernel of Y, or that P is an eigenvector of Y that corresponds to 0 eigenvalue. And now I can use its decomposition from the first point, right? So I can say that now, because Y is a positive semi-definite matrix, I can write Y as ML M transpose. And here I'm going to, again, I'm not going to use anything sophisticated. So I'm just going to look at this decomposition. Let's say this is a diagonal matrix. So my eigenvalues are ordered. So some of them are, of course, 0 because, or they would be 0 if something here is non-zero. So I will have one of those matrices like this. with those columns corresponding to eigenvectors for non-zero eigenvalues. Then I will have my matrix L, and here we'll have non-zero eigenvalues, and here we'll have zero eigenvalues. And let me call it M. Here I will have the rest. That looks like this, right? So some M bar transposed, that corresponds to M transpose. So basically, right, so because now what happens is, if I have a zero eigenvector, an eigenvector that corresponds to a zero eigenvalue, they all will live here. Eigenvectors for zero eigenvalues. Right, so I can remove all them and just use this truncated matrix. Something like this. Okay, so now I have my original matrix Q. So the kernel of Qt is, so everything in the kernel of Qt is in the kernel of Y, and it has to be in the kernel of M bar by this construction. Will be in the kernel of M bar. And then because kernels of matrices, M bar transpose, kernels of matrices are orthogonal to the images of transposed matrices, I will have the image of M bar subset of the image of Q. And then I can represent M as, say, QA, right? Because I will be representing the columns of the matrix A, so the columns of the matrix Q. And then from here, I have the representation Y equals QAL A transpose Q transpose. So this will be a positive semi-definite matrix. It's very easy to check, right? By just multiplying on the right and on the left by some vector. And it will belong to SK plus because of the dimensions here. So this matrix is, what was it, N by K. So A will be K by R. And so this means that Y is an F, right? So we use the representation from the definition of F. Right, so this is just demonstration, right? How to show that how to study faces of structured convex sets. Right, so we conclude from here that F is a face of K, or of the cone of positive semi-definite matrices. And I didn't do it with zero, but for zero face, the construction is very similar. So I have shown that this is a face of my set, but I don't know whether there's anything else. And there's other valuable things about faces and valuable things we know about convex sets that allow us to actually prove those things very easily. So I have determined that something like this is a face of a cone of positive semi-definite matrices, but I don't know if there's any other faces. And we'll show later that there's no other faces, right? How to show, it remains to show that there's no other faces. And for this, we can use the idea of a minimal face. And really minimal faces are used, let's say, whenever minimal faces are used, they are very basic and extremely valuable. Sometimes I think sometimes proofs are written without the use of minimal faces where they could be used, and that can make things very complicated. So, and again, if anybody has any questions or corrections, additions, please use the chat. So what is a minimal face? Now, I can pick any point in my convex set and then take all faces of that convex set that contain this point. So on this picture of a triangle, right, I will pick, if I pick an X on a boundary like this, I take the triangle and I will take the edge of this triangle. So there's no other faces that contain this point. So the intersection will be the edge that contains the point X, right? So minimal faces are well defined, of course, because if I take any intersection of faces of a convex set, any intersection of faces will be a face, right? So if I take any collection of faces of some convex set C, then the intersection of all those faces in this collection will be a face of C. Why? Because of the definition, right? So because of the definition, if I check the definition, so look at this intersection, and I take any line segment in my set C that has an interior intersection with this set, right? Because it's the intersection of faces, it should belong to each one of those faces in this intersection, right? So it's very clear from the definition that the intersection of faces is a face. And also, of course, if there is a smaller face than this, it is impossible because then it has to be inside this intersection, right? So if there is a smaller face B, containing X, well, then, of course, the intersection of all faces that contain X should be contained in the space as well, right? So it contributes to this intersection. So there's a contradiction. So a minimal face is the intersection of all faces that contains the point X. It's also actually the smallest face of the convex set that contains X. And we have useful characterization, which is not like it's not difficult to prove this characterization, but it's not exactly the same as the definition of the face. So to get the minimal face of any point in the convex set C, we can't just collect all line segments from the set for which X is on the open line segment connecting those two points, right? So we gather all that, and that gives us the minimal face. Oh, that's a great question from Lyndon. Yes, Lyndon, it is true that the characterization of the counterpoint semi-definite matrices, here you can have orthonormal columns. Yes, actually, I will mention this. I hope I will mention this shortly, because when I go the other way around, you'll see that somehow yes, it will be clear that yes. So, and also, yeah, let's not dwell on this, but it's true. Yes, you can use orthonormal representations. So matrices that have all columns of those matrices will be one and orthogonal to each other. Okay, so now let's talk about the relative interior. In the basic convex analysis books, like say all the books, relative interior is usually defined as the interior of a convex set with respect to the affine hull. So you take the smallest affine subspace that contains the convex set, for instance, a line or a hyperplane, right? It's a linear subspace that can be also translated in the space. And you take the interior with respect to this set. There's a lot of equivalent definitions of relative interior, and I will talk about that in my third lecture, and also I will talk about that in infinite dimensional spaces. But I like the definition of the relative interior that looks like this. So the relative interior of a convex set C is the set of all points for which the minimal face coincides with the set C, right? So again, I look at that triangle, right? If I am somewhere in the boundary, the minimal face is the edge. If I am really in the interior of this triangle, the minimal face will be the whole triangle, right? So I can see it from the definition of the face or from that characterization, right? If I take everything, all line segments that have X in the interior, then I will get the whole set. So in finite dimensions, relative interior of a non-empty convex set is always non-empty. I don't think I'm going to do a proof of this, but maybe for an idea, right? I take some convex set. I pick a point in this convex set. It's not empty, so I can pick it. And then I take, some kind of a spanning set, or let's say maximal linearly independent system of vectors. Take some points here, y1, y2, and so on, like k, right? So that C minus X is a span of these guys. Right, and there is nothing else. And then somehow the point in that simplex, right, if I pick the linearly independent maximal system, will be in the relative interior, or will have the face, the set C as a minimal face, right? Because no matter what line you consider through that point here, that stays within this kind of span that you construct of the set C. There will be a line segment there, right? Well, you can, for any point, you can somehow overshoot past C. Okay, there's more interesting things, so let's not look at this too much. So a really cool thing is that we have a decomposition of a convex set into relative interiors of its faces. And also this decomposition is disjoint, right? So if I take, again, my triangle, it's a very basic example, but still. So what will this decomposition look like? I will have the relative interior of my triangle. So this is all points for which the entire triangle is the minimal face. Then I will have all my sides of the triangle, right? So they are the relative interiors of the edges, and then I will have the vertices. So it's a disjoint decomposition because none of those things intersect. And it's just extremely useful because there is pretty much nothing else in a convex set but its faces, and having a disjoint decomposition is a really neat thing, right? So it's used all the time in proofs and in reasoning about convex set. So if I want to show that it really holds true, right? So the first thing I can do is just take any point in my convex set. And then, of course, for every point, I have a minimal face. Of course, the minimal face is not empty, right? Because it's the intersectional faces that contain the point. So at least it contains point itself. So the minimal face is non-empty. It contains X. And also, it has non-empty interior. And by the definition, by the definition of relative interior, X has to be in the relative interior of the minimal face. So let's write it like this. Right, so already we have decomposition because for every X, there's a minimal face and X is in the relative interior of the minimal face. So we have this decomposition into relative interiors of faces. And to get a disjoint, we can use the fact that the relative interiors of minimal faces do not intersect. So if I have two faces of the same set, right, and suppose that they're different, then I want to show that the relative interiors do not intersect. So suppose that there is some X that is in the both. So it's in the relative interior of E and also in the relative interior of F, right? That's the intersection. So that means that for X, E is the minimal face of X and E, and F is the minimal face of X and F. However, because these guys are faces of the same convex set, right? So because intersections of faces are faces, E intersected with F is also the face of the convex set C, but also because of faces of faces, and also it's like if a subset of a face is the face of the larger set, it's also a face of a face. So these guys will be faces of E and F. So then, because of the definition of the minimal face, this should be the subset of this, and this should be the subset of the same thing. And so, of course, then we have a contradiction with this inequality, right? So it should be the same as F. So relative interiors have empty intersections, and that's why we can put this dot here, right? So it's a disjoint union. So let's go back to the SDP cone. And it will be really helpful if the organizers tell me how much time I have left, because I didn't record when I started because it was a little late. So I'm not sure how much time I have to continue with this. So let's maybe, yeah, you could let me know in the chat. So let's go back to the SDP cone. And I think in the course of this discussion, we'll address the question from Lyndon also. So remember, we have shown that all these guys are faces of the cone of positive semi-definite matrices. So how can we see that there's no other faces? So a very simple way to see that there's no other faces is to use that disjoint decomposition into relative interiors, right? So around 5 minutes. Oh, okay. I think I'll only have time to finish this then. Well, everything else will have to be done next time. Okay, so it somehow shows the basic technique that we can use to list faces of a convex set. Because sometimes it can feel really difficult. How do I list all faces? Should I use some topological results or something like this to just cover the entire surface? But actually using minimal faces, it's very easy, because what you do, you simply for every matrix in this cone, or for every point in the set, you simply construct a minimal face, and then that's it, because there is nothing else in the convex set. So every face in the convex set has non-empty relative interior. Yeah, so because we have this decomposition, right? So every face has non-empty relative interior, and if for every point I produce a minimal face, I have listed all faces. So basically, for every point in this cone, I should get the minimal face. And if a minimal face looks like this, there's no other faces left. And then let's use the decomposition into the orthonormal matrix and the diagonal matrix. So X is M, L, M transpose, right? M is orthogonal. And again, I can use the same trick. So I can here take my M and only take the part of M that corresponds to a eigenvectors that have non-zero eigenvalues. Take my L, do the same thing, extract this M perp here. So I have something like that. And now I have positive definite matrix here. It doesn't matter that these matrices are orthonormal, but well, they're no longer orthogonal, but they contain, right, columns from an orthogonal matrix. Now what I can do, I can say, okay, now if I take all if I pick any matrix from the face that corresponds to this matrix M bar, right? So if I now let Q equal M bar, then, and I consider this set, M bar U M transpose, and U will be in whatever K by K block of non-zero eigenvalues I have. Then if I have a positive semi-definite matrix that lives in that space of symmetric matrices, K by K symmetric matrices, right? So I take my U, and it's positive semi-definite. No matter what other matrix I pick, that is positive semi-definite, right? I can always draw a line segment through this positive definite matrix and get some positive semi-definite matrix on the other side, right? It cannot happen that I have this kind of convergence of negative definite matrices to a positive definite matrix. That would make this positive definite matrix positive semi-definite, right, at least. So, and because of that, right, so anything I pick in here, right, it will be an endpoint of some line segment that goes through this U and continues beyond U, right? So this shows that any minimal phase that contains X should contain F, right? So F mean of X should contain F. And that's it, right? So then, okay, so F has to be minimal. And there is nothing else, right? Because for every point, we choose the minimal phase. I think I have run out of time. I wanted to say more. Let me talk about semi-definite programming, and then maybe tomorrow I will continue. I think I have miscalculated how much time I will need. So let me continue tomorrow with this, and let me just say a few things about semi-definite programming. That so a semi-definite program has a linear objective function, right? And constraints that consist of some kind of semi-definite constraint. So you would have variables and matrices, for example, and they will have to be positive semi-definite, and linear constraints. It can look like this. So here, for example, I have a trace product. So that simply, I mean, in a sense, it means that so it's kind of like a scaled inner product, or it is an inner product on the entries of the matrix. And so that because the trace is just the sum of diagonal elements, it gives a generalization of the product that we use for linear programming, right, for matrices. Or we can have a formulation that looks like this. And here also there's a linear subspace and positive semi-definite constraint. And I think I will talk about vectorhedra next time then. So feasible regions of semi-definite programming problems are called vectorhedra. And the importance of semi-definite programming is that, first of all, we have methods for solving them. There's software packages available for solving semi-definite programs. They work very well with duality. I hope to mention this also. And they're used in a very broad range of applications. So the most interesting applications are probably performance estimation and optimization of algorithms, which in modern times is very cool. So you can look at some classes of optimization methods and fine-tune the parameters by using some definite programming problems. They are very common in those models in solving very hard combinatorial problems approximately. And a very interesting thing about those relaxations of combinatorial problems is that you can get, in some cases, guaranteed bounds. So somehow you would relax the problem obtain an optimal solution to that relaxed problem. Sometimes the difference between the relaxed solution and the actual problem is the matrix rank or something like this. So you could get a matrix that is higher ranked than the original combinatorial problem, for instance. And then you can get an approximate solution. So not an approximate, yeah, you can get an approximate solution to the combinatorial problem by taking cuts or doing all sorts of things with the semi-definite solution. And also there is bound. So for example, for the max cut problem, there is a bound that tells you that you are within some margin of error from the actual optimal solution. And that's very valuable for a problem that is NP hard or NP complete. And something that I think was talked about before is that you can get certificates of non-negativity in polynomial optimization using semi-definite programming. You also have all sorts of hierarchies and approximations using SDP to polynomial problems that converge to solutions and so on. All right, so let me, maybe, should I stop here and continue tomorrow? Let's look at the spectrohedron and maybe I will stop.
Yes,
so
yes. Take your time for the spectrohedron and then maybe we stop.
Okay, so let me talk about spectrohedron and then that's it. So spectrohedra, a very good example of a very structured convex set. So of course, in general, spectrohedra are solutions of feasible regions of semi-definite programs, right? So you have a linear constraint and semi-definite matrix constraint. So how does it somehow translate in geometry, right? So if we have if the linear subspace constraint or affine subspace constraint is three-dimensional, right? We can get a picture like this. But for this example, I just want to relate, right, a picture and somehow the object to how it is a spectrohedron. So here I have an elliptic that is three-dimensional set, and it's defined like this. So I take a matrix, symmetric matrix, I put some definite constraint here, and some of the integers of my matrix are my variables, and I put ones on the diagonal that give me a linear constraint, right? So that will be like I equals 1, right? So that's a linear constraint, and everything else is a semi-definite constraint. So how does it translate into this object? Well, what I will do to see it is I will use something like the Sylvester criterion, right? So I will look at the determinant of this matrix. So I will calculate the determinant of this, right? So it will be like 1 minus 2 x, y, z plus 2 y, z minus y squared minus x squared minus z squared, right? So this thing will actually give me an algebraic variety that contains the boundary of this object. So I will have to restrictors to be non-negative, and then I will take all principal minors of this matrix and calculate their determinants. And so I will have something like 1 minus x squared greater or equal to 0, 1 minus y squared greater or equal to 0. And that will chop off the bits of this variety that corresponds to the determinant and give me this object, right? Okay, so let me finish here and continue tomorrow, probably.
Yeah, thank you so much, Vera. That was a fantastic start into our series. Yeah, are there maybe any questions from the audience? Please either unmute yourself or put it in the chat.
So can I ask a question?
Yeah.
Yeah, I think my question relates to Linton's question. So, but maybe it's a different one. So, but it's around this area anyway. So, in the problems with, say, eigenvalue decompositions, so indeed, we would normally use the matrices with orthonormal columns, so to make sure that they're not just orthogonal, but they are also unit vectors. So, and I just was wondering, is it essential that, I mean, obviously, if the columns are orthogonal, so it will work for orthogonal unit vectors as well, but is it actually essential for your problems? Because what actually will happen, you will multiply something by, I don't know, a squared. And since it's, a non-negative number anyway, so maybe it doesn't affect. So we don't need to worry about normalization. Or is it essential? So that's probably what I would ask. But maybe it's not the same what Lyndon was asking.
Well, it's vague, right? So I'm not sure. So for some problems, it's important that you have some kind of
Sorry, somehow I can't hear Vera. Maybe I disconnected somehow.
Sorry, what happened? So okay, so it seems that we can see Nadia, but
What happened?
okay. So I would say that, so this was a very specific thing, right? So it was just the geometry of the cone of positive semi-definite matrices. So somehow for that particular geometric thing, right, you are trying to represent faces. It doesn't matter because it's this transformation with, so if you take a non-singular matrix, right, n by n non-singular matrix, and you write something like this, n by n non-singular matrix time multiplied by x, and then the same thing transposed. So this is it's an automorphism of the cone of positive semi-definite matrices, right? So if I take this for any x in the cone, that will be exactly the same as the cone itself, right? So from that perspective, somehow here it doesn't really matter because things are the same. But of course, in some problems, it may be important that you represent something through orthogonal matrices, because especially when you talk about things like projections and things like this, it's important to have that thing, right? So projections may not work even on some very nice object. If I somehow stretch it, apply some affine transformation, then things will fail.
Yeah, but for the problems you are going to discuss here, it doesn't matter. So we don't need to worry about normalization. Getting units, so it's okay.
Yeah.
Okay, so the second question, what kind of software do you use for drawing all these pictures? Because it really looks impressive.
So I wanted to actually show you but I think I have miscalculated my time. So let me run. So this particular one is done in Mathematica. I was going to run Mathematica and show you, but let me try to change to a screen. I'll change to a screen. So you should be able to see Mathematica now, right? And something like this is actually very easy to draw using Mathematica. So I would do something like I will define my matrix. So let's just write down this matrix that defines the set x, 1, z, y, z, 1. Now I will just draw the thing, right? So I will draw the determinant, determinant less or equal to 0. We'll take the determinant of m less or equal to 0. I have to write some constraints here. Oh, greater or equal to 0, sorry. That's consistent. Okay. Right. So that's it, right? And then you can change things a little bit. So you can remove the mesh. You can also make it better somehow. So if you try to draw something like I have on the slide, it will take more time. You need to adjust somehow some parameters, right? And then, so since I was showing how to do this, let's also add 1 minus x squared greater or equal to 0, right? To actually get the spectrohedron, right? So that's the thing.
Yeah, thank you. Thanks.
And I think Julian was asking a question, but I don't know. I missed the question, so I don't know what.
I put my question in the chat, but basically it was about. Can you hear me? Yeah.
Yeah.
It was about the your proof. So you rely on the fact that every face is the minimal face of some point.
Yeah.
In your set.
Yeah.
Okay. But you haven't proven that fact, or you have?
No, it follows from the decomposition. So it follows, yeah, it follows from here. So first of all, so the set is a disjoint union of relative interiors.
Yeah.
But also every face has a non-empty relative interior. Right. So
okay.
Yeah.
Okay,
So if you
okay.
pick any face, it will be in the decomposition.
Yeah. Okay.
Yeah. And I must say that somehow those things, they, like when you look at them like this, they seem, they're very classic and they seem obvious, but it's easy to forget about this. And sometimes when you try to actually describe faces, things can get very complicated if you don't think about that. Because, I mean, to me, at least, when you work constructively with convex sets, that's the best way to list faces. So you pick every point from the set and just demonstrate what is the minimal face, and that's it.
Okay, that makes sense. All right, thank you.
All right, I think let's thank Vera again, and let's call it a day for today. Very nice, thanks.
Yeah, thank you. Also, tomorrow, do we connect using the same link?
Yes, tomorrow, same time. And regarding the link, I think we send a message.
Okay.
So please take a look at your inbox for finalizing this the Zoom link. And yeah, sorry.
Yeah, and we'll probably update the website. So if you are registered, then you will receive an email. Otherwise, you can have a look at the website, but maybe you register. Maybe that will make everything simpler.
Well, about the link, because I think I haven't started the link before 11 o'clock because